In this presentation, we'll introduce the basic concepts of a fluid power system. There's 7 main components. There's a reservoir where the fluid is kept. There's a filter to keep it clean, a pump to increase pressure. If the pressure gets too high, there's a pressure regulator, which would release some of the pressure. There's a control valve that manages which direction the fluid is flowing. And then there's a cylinder and an actuator. The fluid can be a gas or a liquid. If it's a gas, it's called pneumatics. If it's a liquid, called hydraulics. Let's look at how this works. Basically, you build up pressure in the cylinder and it pushes the actuator. It allows the actuator to do work. From the reservoir, the pump would pull either the gas or the liquid, the fluid, through the filter, into the pressure regulator, through the control valve. It would increase the amount of fluid inside the cylinder, which would then push the actuator or the piston, in this case, push it out or up. Then the reverse occurs. The actuator can do work in this direction as well, but the actuator is being pulled back into the cylinder as the fluid is pumped out through the control valve to the reservoir. When we put this whole system together, we can see that we can do quite a bit of work with the actuator either moving in or out of the cylinder, and that's all in how the fluid is being controlled. If the fluid turns out to be a gas, then we call it pneumatics. Pneumatics tend to be really fast and clean. Here's a nail gun that's tethered from an air compressor. That's a good example of a pneumatic system. Then we also have hydraulic systems. That's when the fluid is a liquid. And hydraulics are very strong and very smooth. And right here we show an example of a track hoe. Here's an example of a fluid power system that you might see working at a car repair shop. In 3.2, what we're going to do as engineers is study the laws that govern the design and effectiveness of a fluid power system, such as what work can be done given a set of constraints of cylinder size and pressure generated by the pump and those kinds of things. So dive right into these laws and learn how to design these systems.
Let's start by going over some of the basic principles of fluid power. First, we have energy, which we've studied previously, the ability to do work. And in fluid power, we have an additional concept called energy transfer, which is a cool part of fluid power because it allows us to produce the energy in one location and use it in a different location by transferring it. Here's an example we're going to study a little bit. Let's start by looking for the input device. So the input is where that energy is initially created. So the input source here, you can see that there's a reservoir at the bottom, and then that M indicates the motor that's attached to the pump that is going to push the fluid out of that reservoir. And there's a gauge on there as well that will tell us what the pressure is. The output device in this case is some sort of a lift. So think maybe a car repair garage or something like that. So in this case, we're told that the system's output device lifts 8,400 pounds, 6 feet. So if we want to calculate how much work is performed, if you recall, the formula for work is force multiplied by distance. So in this case, it would be 8,400 pounds times 6 feet. And we were given the right units initially, so we can just leave those as they are. We don't need to worry about converting. And we have 50,400 foot-pounds. We're also told it took 10 seconds to perform the work. And that piece of information allows us to figure out the power or rate of doing work, which is work over time in seconds. So we just take the 50,400 foot-pounds, divide it by 10 seconds, and we are able to determine that 5,040 foot-pounds per second is the amount of power that this system is producing. So we've determined the amount of work in foot-pounds. We've determined the amount of power that the system is outputting in foot-pounds per second. What if we wanted to figure out how much power is going into the system initially? in order to figure out the hydraulic power, because this system is a hydraulic system, we're going to multiply the flow times the pressure. And so we're told that the input source is flowing at 12 gallons per minute, and the pressure is 1800 psi, or pounds per square inch. So we're going to just multiply those together. 12 gallons per minute times 1800 pounds per inch squared equals 21,600 gallon pounds per minute inch squared. Can we easily compare the input power to the output power? You'll notice that our output power was determined in foot-pounds per second, and our input power that we just calculated here is gallon-pound per minute inch squared. So no, that's not something that we are going to be able to do at this time. So we've determined the output power in foot-pounds per second. We've determined the input power, or hydraulic power, in gallon-pounds per minute inch squared. We need to find a common unit of power so that we can compare these and figure out how efficient the system is. Horsepower is what we're going to use for the common unit of power. And in order to convert to horsepower, we have two conversion units. First, 1 horsepower is equal to 550 foot-pounds per second. And then for the hydraulic power, we have 1 horsepower is 1,714 gallons per minute psi. So let's do the output device first. So here's the equation here for the power output converted to horsepower, and we find that we have 9.2 horsepower in the output. And then we convert the input, or hydraulic power, and use this equation here with that conversion factor, and we find that we have 12.6 horsepower. So we've converted both the input and output power to comparable units. They're both in horsepower. We need to figure out the efficiency of the system. So in order to figure out the efficiency, we use the Greek letter eta to symbolize efficiency, and we compare the power out to the power in and multiply it by 100% to make it a percentage. So in this case, our efficiency is 9.2 horsepower output over 12.6 horsepower input times 100% is 73% efficient for this system. Let's take a look now at Pascal's principle, or Pascal's law. It states that the pressure applied on a confined fluid acts with equal force throughout the fluid and to the walls of the container, where the pressure is the force divided by the area. Looking at this example here, we have some sort of a hydraulic lift. And according to Pascal's principle, the pressure in the fluid in this yellow area is equal everywhere. So let's say, for argument's sake, that our pressure is equal to 2. All right, we're not going to use units, we're just going to use a really simple example here that will help you to understand the principle. So if the pressure of this fluid is equal to 2, according to Pascal's principle, that pressure is the same everywhere. So P1 is also equal to 2, and P2 is also equal to 2. All right, now let's say over here, our F1, we'll keep things really simple. What if our F1 was equal to 1? So F1, the force applied here, is equal to the pressure 1 times what area? So that area in this case would have to be 1/2 of whatever our units are, 1/2. So now we're told that the second force is 10 times as large as the original force. So the original force was 1, so our second force is going to be 10 times that, so it'll be 10. If our second force is 10, then the pressure is 2, then the area of the second one would be equal to 5. So this here shows you how we can apply a small force on this side, push it on the original force, pushing down with a smaller area, and it will result in a much larger force pushing up on the other side if the area on the other side is much larger. Let's look at an example of how Pascal's law might be applied. We have a pneumatic cylinder here, and we're going to try to answer the question, how much pressure can be produced by the pneumatic cylinder? First of all, the purple arrow is showing you where the force is being applied, and the force here is 120 pounds. The red arrow in corresponding area is compressible gas, and the blue area in corresponding area is also compressible gas. The white arrows show the direction of the force and point to the piston head, which has a diameter of 6 inches. So which of the red or blue areas is going to be compressed or under pressure based on the scenario we're looking at here? So because those white arrows are pushing the piston towards the blue area will be the one that's compressed. So looking at this cylinder here, let's figure out how much pressure. Step one, we're going to identify the formula. We're going to use the formula for Pascal's law that it's based on, which is pressure is equal to force divided by area. And step two, we'll identify the units. Our force is in pounds and our diameter is in inches. A good idea right at this point is to take a quick look and see if we need to convert anything, and we're good. These are the units that we want to be using. Step three, we're going to identify the known information. We have the force as 120 pounds and the diameter is 6 inches. Step four, let's figure out what our unknowns are. We need to find the area before we can find the pressure, which is what we want in the end. Which formula do we need? We're going to start off with the area formula, just the area of a circle, which is pi r. So for the area of a circle, make sure that you use the radius, not the diameter. So our diameter was 6 inches, so our radius will be 3 inches. We put it into that formula, and we have our area as 28.27 inches squared. It's a good idea when you do problems like this to not round until you get to your final answer. Step 6, we'll solve for the pressure. Our pressure is force over area, so 120 pounds over 28.27 inches squared. And we find that our pressure is 4.24 pounds per inch squared.